We are now moving on from temperature to precipitation, and this is Unit 5B. Here are the 5B learning outcomes, so go ahead and pause the video and write these down. Here are some key topics that I want you to pay attention to as you're watching the series of videos in this section. The phases of water and the latent heat of water are going to be covered a little bit in this video, but then also in videos 5B.2 and 5B.4. So pay attention to those concepts. Humidity and dew point will be covered in video 5B.3. In this video, I will cover processes that make air rise. Then in video 5B.5, you'll learn about adiabatic heating and cooling and cloud formation. Finally, in the last video in Unit 5B, we'll talk about the types of precipitation. So let's start with the phase changes of water. A phase change is when something goes from a solid to a liquid or a liquid to a gas. And I want to make sure you're familiar with not only the names of these different processes, but also a little bit about which processes absorb energy and which ones release energy. That will be very important when we start talking about weather. So the first one I have here is a change from liquid to a gas, and that is called evaporation. Calories are units of heat energy, and it takes 600 calories per gram of water to make evaporation occur, and that's called the latent heat of vaporization. The main thing is that energy or heat is absorbed when water evaporates to a vapor. The other direction of this phase change is from water vapor, which is a gas, to a liquid, and that's called condensation. And in this case, energy is not absorbed, but energy is released. And that's going to be very important when we talk about hurricane formation, because condensation occurs and releases a lot of heat that fuels the storm. Now let's look at changes between solids and liquids. If we go from a solid to a liquid, that is called melting. This is also a process that absorbs energy. Think about it if you had an ice cube in your hand. The ice cube will melt, and the reason the ice cube will melt is because it's getting heat, energy from your hand. So it's absorbing the heat. On the other hand, if we go from a liquid to a solid, which is freezing, heat is released. And this one is not as obvious, but it is the case. What about the idea of going directly from a gas to a solid, or a solid to a gas? Can we do that? Well, yes, we can. Going from solid directly to a gas is called sublimation. And one example of sublimation is if you happen to have one of those freezers where you make your own ice in ice trays, and one of those trays gets kind of pushed to the back and forgotten about, and then later you dig it out. Those ice cubes might be smaller than normal, and it's because they sublimated. They went from a solid directly to a gas in the freezer. They didn't melt. They didn't have a liquid part. They sublimated. Another example of sublimation is those little smelly things that sometimes people put in their house, in their bathrooms. You open them up and they look like they're wax of some sort, and they give off an odor, and then over time they're gone, right? And there's no melting. They don't melt and then go into a gas phase. They go directly from a solid to a gas. So that's another example of something that sublimates. Going from a gas directly to a solid is possible, and it's called deposition. These days we have frost-free freezers, but in the past, frost used to collect on the box of the freezer on the inside, and every once in a while you'd have to defrost the freezer and get those big chunks of ice out, otherwise your freezer would get smaller and smaller with all this ice piling up. And that is from water vapor in the freezer that deposits directly onto the sides of the freezer. There's no liquid phase in between. So here's an example of sublimation. Now this is not water, but this is carbon dioxide or dry ice. And inside the pumpkin is a chunk of frozen carbon dioxide that was kept under some sort of condition so that it was nice and cold. Once it experiences room temperature, it sublimates directly into a gas. There's no melting. Now, you're not actually seeing carbon dioxide gas here because that's invisible. What you're actually seeing is water vapor from the atmosphere, which is invisible also, turning into a liquid, condensing, as a result of the cold temperatures being produced by the carbon dioxide gas. So that's a little complicated. But for sure this is an example of sublimation because you're going from a chunk of carbon dioxide ice to a gas. Frost is an example of deposition. So this is not frozen dew. This is when super cold water vapor, which again is a gas that you can't see, contacts a surface like a window, and it directly deposits upon it. It freezes right on it. So here's a summary diagram showing all of these, and this is a good thing to kind of look at. There's another version of it in your textbook that I'm not too crazy about. It's a bit busier. But you can see we're going to go from a solid to a liquid, and the red arrow indicates we're going to absorb heat. So this is just like having that ice cube on your hand. It's going to absorb heat, and it's going to melt. If we go from a liquid to a gas, it's going to evaporate. And notice it takes a lot less energy to melt ice than it does to evaporate liquid water. And that's because of the energy necessary to break bonds. Here we have solid water, that form of ice, and then here we have liquid water where the H2O molecules are just rolling around in the water. And going from this to this stage requires a lot less energy than going from this stage to getting those water molecules completely independent of the water and flying around in the atmosphere. Notice that sublimation, which goes directly from solid to gas, also absorbs energy, and the energy necessary is pretty much the sum of these two processes. Going in the other direction, from gas to solid, we can go directly using deposition, or we can have condensation and freezing. So now let's talk about processes that lift the air. Now, why do we care about that? Well, we care because when air rises, it forms clouds, and then it forms rain, and that produces weather, and so we're going to be talking quite a bit about rising air. So what is it that naturally makes air rise? The first one I'm going to talk about is orographic lifting. Now, that sounds like a fancy word, but oro, O-R-O, means mountain in geology. So it has to do with mountains getting in the way of the wind, basically. So in comes the airflow, it bumps into these mountains, it has nowhere to go but up. So up it goes, it produces clouds and possibly rain. And so when that air gets over the mountain to the other side, it is now dry air. All the moisture has been rained out of it. And then we often get something called a rain shadow desert on the leeward side of the mountains. So here's a quick definition. And here's an example in California. Here we have wind that comes in from the Pacific. When it reaches the mountain range of the Sierra Nevadas, it has to go up and over. And so this is where a lot of rain occurs in the western Sierras, and then you can see all of these rivers that drain down to the Great Valley where we produce a huge amount of food. Once that air has gone up and then comes back down, the air is very dry. And so this first valley right here that it comes down into is shown over here. It's Owens Valley. So you're standing in the valley looking west, basically standing at this point of this red arrow looking to the west. And everything in the foreground is very, very dry, and the valley is very much like a desert. A second process is called frontal wedging, or when warm air gets pushed up over cold air. And that's because cold air is more dense, so it acts like a barrier. These are called cold fronts and warm fronts, and we'll be talking about these and something called a mid-latitude cyclone next week. Here are some cartoons of cold fronts and warm fronts. Here we have the warm air being pushed up and over cold air, again because cold air is more dense. Here we have the cold air, which is actually moving faster than the warm air, and it's pushing warm air up. So in both cases, warm air rises, forms clouds, and rains. Next, we have convergence. In some cases, there are places where winds come together, and then they bump into each other, and they have nowhere to go but up. So here's a definition. They flow together and rise. This creates low pressure, and we're going to talk about pressure next week. It'll be very important. A little preview, rising air creates low pressure. So in Florida, this is commonly an occurrence where we have winds coming from the Gulf of Mexico, winds coming from the Atlantic Ocean, and they bump into each other and rise and form clouds. And down here you can actually see, here's Florida, you can see it outlined by the clouds, and here the ocean and the Gulf are fairly free of clouds. A fourth way that air can rise is called localized convective lifting, another mouthful. But what this means is that some areas get very warm, possibly because of their albedo. Remember I talked about how a dark colored surface absorbs a bunch of sunlight, so a dark forest might wind up being a little bit warmer then a nearby snowfield that's white and reflects light. So this is a local phenomenon. This is showing time from left to right, and we have the sun heating some area for some reason. This warm air rises relative to the air around it, and eventually it might form some clouds. These are sometimes called thermals. I used to work with a professor in my graduate days who, for fun on the weekends, would fly gliders. And gliders are airplanes with no engine. So you get towed behind another plane, you go up, and then that plane lets you go, and then you ride the thermals down. You ride and ride and ride. And so he would say to me, oh, I'm going to go flying this weekend because the thermals are going to be good. So if you're going to fly without an engine, it's good to know that there's going to be a lot of local rising air to give you a decent ride. The next 4 videos you're going to watch are on water phases, relative humidity, the heats of water, and this is going to introduce a concept that I've already talked about, but I didn't give it a name, so I'm going to do it now. It's called heat capacity. Remember I talked about how land heats up and cools down more quickly than water. The concept behind that is heat capacity. Heat capacity is the resistance to change temperature. So water has the highest heat capacity of any substance because it's very resistant to changing temperature. Land has a lower heat capacity because it changes temperature more readily. Metal, like the metal of a cooking pot, has an even lower heat capacity because it changes temperature very quickly. So that's heat capacity, and you'll learn about that in that video. And then finally, you'll watch a video on clouds and patterns of the weather. After that, I'll finish up with a video on precipitation, and next week we'll move on to winds and air pressure.